The step-deviation method. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lessons, we explored how to calculate the mean using the direct method and the assumed mean method. Now, you might remember that while the assumed mean method is a great step forward, because it helps reduce the size of the numbers we have to work with, it isn't always perfect. If you are dealing with a very large class size, you might still find yourself struggling with quite large values when calculating the sum of f sub I times d sub I. This can make the arithmetic a bit tedious and increase the chance of making a mistake. That is exactly why we are introducing the step-deviation method today. Think of this as a further refinement of the methods you already know, specifically designed to simplify your calculations even more. This method is particularly powerful and useful when your class intervals are of equal size and when the deviations, which we define as d sub I equals x sub I minus, share a common factor. By dividing these deviations by that common factor, which is usually the class size, denoted as h, we transform those larger numbers into much smaller, more manageable integers. This makes your work much faster and significantly reduces the likelihood of making those frustrating arithmetic errors during an exam. So, let's take a closer look at the formula that makes this possible. The mathematical formula. Now that we understand the purpose of this method from our previous slide, let's look at the mathematical formula that makes it all work. To find the mean, which we denote as x bar, using the step-deviation method, we use this formula. X bar equals a plus h multiplied by the quantity, the sum of f sub I times u sub I, all divided by the sum of f sub I. It might look a bit intimidating at first, but let's break down each component so you know exactly what to plug into your table. First, I represents our assumed mean. As we mentioned earlier, this is a value you'll pick from your class marks, usually the one right in the middle. Next, h is the class size. This is simply the width of your intervals, the difference between the upper and lower limits of a class. Now this is the most important part of this specific method. U sub I is the step deviation. We calculate this by taking the class mark, x sub I, subtracting our assumed mean, a, and then dividing that entire result by the class size, h. By doing this, we shrink our numbers down to much smaller, more manageable integers. Then we have f sub I, which is just the frequency of each individual class. In the numerator of our fraction, we have the sum of f sub I times u sub I. This means you'll multiply each frequency by its corresponding step deviation, and then add all those products together. Finally, in the denominator, we have the sum of f sub I, which is simply the total frequency of all the classes combined. In the next slide, I will walk you through a step-by-step procedure, so you can see exactly how to organize these values into a table and apply this formula correctly. Step-by-step procedure. Now that we have seen the formula, you might be wondering how to actually apply it to a problem. Don't worry, it looks complex, but if you follow these manageable steps, the calculation becomes very straightforward. First, we need to find the class marks, which we denote as x sub I. To do this, look at each class interval and calculate its midpoint by adding the upper limit to the lower limit and dividing the result by 2. Second, you need to choose an assumed mean, which we call a. You can pick any value from your x sub I column, but a great tip is to choose the middle value to keep our numbers balanced. Third, determine the class size, represented by the letter h. This is simply the width of your intervals. For example, if your interval goes from 10 to 20, then h is 10. Fourth, this is where the step deviation part comes in. For every class mark, you will calculate u sub I. You do this by taking the class mark, subtracting our assumed mean, and then dividing that entire result by the class size h. This is what shrinks our numbers down. Fifth, once you have your u sub I values, compute f sub I times u sub I. This just means you multiply the frequency of each class by its corresponding step deviation. Sixth, we need to sum everything up. Find the total sum of all those f sub I times u sub I products, which we write as the summation of f sub I times u sub I, and also find the total frequency, which is the summation of f sub I. Finally, step 7. Apply the formula. You will substitute all your calculated values into the formula. X bar equals a plus h, multiplied by the quantity of the summation of f sub I times u sub I, all divided by the summation of f sub I. If you follow these steps carefully, as we are about to see in our real-world example on the next slide, the arithmetic becomes much easier to manage. First, we need to find the class marks, which we denote as x sub I. To do this, look at each class interval and calculate its midpoint by adding the upper limit to the lower limit and dividing the result by 2. Second, you need to choose an assumed mean, which we call a. You can pick any value from your x sub I column, but a great tip is to choose the middle value to keep our numbers balanced. Third, determine the class size, represented by the letter h. This is simply the width of your intervals. For example, if your interval goes from 10 to 20, then h is 10. Fourth, this is where the step deviation part comes in. For every class mark, you will calculate u sub I. You do this by taking the class mark, subtracting our assumed mean, and then dividing that entire result by the class size h. This is what shrinks our numbers down. Fifth, once you have your u sub I values, compute f sub I times u sub I. This just means you multiply the frequency of each class by its corresponding step deviation. Sixth, we need to sum everything up. Find the total sum of all those f sub I times u sub I products, which we write as the summation of f sub I times u sub I, and also find the total frequency, which is the summation of f sub I. Finally, step 7. Apply the formula. You will substitute all your calculated values into the formula. X bar equals a plus h, multiplied by the quantity of the summation of f sub I times u sub I, all divided by the summation of f sub I. If you follow these steps carefully, as we are about to see in our real-world example on the next slide, the arithmetic becomes much easier to manage. Real-world example. Now that we understand the theory and the formula behind the step deviation method, let's put it into practice with a real-world example. Imagine a logistics manager in a warehouse who needs to find the average weight of 50 packages. Instead of weighing every single item individually, they have grouped the weights into a frequency distribution table. Looking at the table, we have 4 weight categories, ranging from 0 to 80 kilograms, with the number of packages, which we call f sub I, listed next to each interval. To solve this, we will follow the step-by-step procedure I mentioned in the previous slide. Our first task is step 1, finding the class marks, which we denote as x sub I, and selecting our assumed mean, which we call a. To find each class mark, we take the midpoint of each interval by adding the lower and upper limits and dividing by 2. For the first interval, 0 to 20, the class mark x1 equals 0 plus 20, all divided by 2, which gives us 10. For the second interval, 20 to 40, x2 equals 20 plus 40, divided by 2, resulting in 30. Moving to the third interval, 40 to 60, x3 equals 40 plus 60, divided by 2, which is 50. And finally, for the interval of 60 to 80, x4 equals 60 plus 80, divided by 2, giving us 70. Now we need to pick an assumed mean, or a, from these class marks. To make our subsequent calculations as simple as possible, let's choose the middle value, so we will set our assumed mean, a, equal to 30. In the next slide, we will use this value to determine our class size and build our calculation table. Real-world example, continued. Now that we have identified our class marks and selected 30 as our assumed mean, let's move on to step 2, which is identifying the class size, denoted by the letter h. To find this, we simply look at the difference between the upper and lower limits of any class interval. For instance, taking the first interval, 20 minus 0 gives us 20. So our class size, h, is 20. Next, we move to step 3, where we construct our calculation table. This is the most critical part of the process, as it organizes all our data for the final formula. Let's look at the columns. We already have our class intervals, our frequencies, and our class marks from the previous slide. Now, we add a new column for our step deviations, which we call u sub I as we discussed in the formula on slide 2, we calculate this by taking the class mark, subtracting our assumed mean of 30, and then dividing the whole thing by our class size, which is 20. Let's calculate this row by row. For the first interval, where the class mark is 10, we take 10 minus 30, which is negative 20, and divide that by 20, giving us a step deviation of negative 1. Multiplying this by our frequency of 10, we get negative 10 for our final column. Moving to the second row, our class mark is 30. Since 30 minus 30 is 0, and 0 divided by 20 is still 0, our step deviation is 0. Therefore, 0 times our frequency of 15 leaves us with 0. For the third row, the class mark is 50. 50 minus 30 is 20, and 20 divided by 20 gives us a step deviation of 1. Multiplying this by the frequency of 20, we get 20. Finally, for the last row, the class mark is 70. 70 minus 30 is 40, and 40 divided by 20 gives us a step deviation of 2. Multipotentially, 2 times our frequency of 5 gives us 10. To wrap up this table, we need our totals. If we sum up all the frequencies, we get a total frequency, or sigma f, sub I of 50. And if we sum our last column, we find that the sum of f, sub I times u sub I, or sigma f, sub I u sub I, equals 20. We have all the components we need now to plug these into our main formula in the next slide. Real-world example, final calculation. Now that we have completed our calculation table on the previous slide, we have all the necessary components to perform our final step, the final calculation. Let's start by bringing back the formula we discussed earlier in the lesson. To find the mean, x bar, we take our assumed mean, and add it to the product of the class size, h, and the ratio of the sum of f, I times ui over the sum of fi. Now let's substitute the actual values we derived from our table. We chose our assumed mean, a, to be 30, our class size, h, is 20. From our totals in the previous slide, we found that the sum of f, I times ui is 20, and our total frequency, the sum of fi, is 50. So our equation looks like this. X bar equals 30 plus 20, multiplied by the quantity 20 divided by 50. To simplify this, let's first solve the fraction inside the parentheses. 20 divided by 50 gives us 0.4. Now, our equation is much simpler. X bar equals 30 plus 20 multiplied by 0.4. Next, we perform the multiplication. 20 times 0.4 equals 8. This leaves us with a very straightforward addition, 30 plus 8. As you can see, our final result is x bar equals 38 kilograms. This means the average weight of the packages in our warehouse scenario is exactly 38 kilograms. It is quite satisfying to see how the step deviation method turned those larger numbers into much smaller, manageable decimals, making this final arithmetic very easy to complete. Key takeaways. Now that we have worked through our practical example and seen how the numbers become much more manageable, let's wrap up with some key takeaways to solidify your understanding. First, let's look at the purpose of this method. As you saw in our calculation with the package weights, the primary goal of the step deviation method is to minimize the size of the numbers we handle. By dividing our deviations by the class size, we transform large, cumbersome values into small, simple integers. This makes the entire calculation process much faster and, more importantly, significantly less prone to arithmetic errors. In terms of efficiency, keep in mind that this method is most effective when your class intervals are of equal size and when your class marks, or x sub I, are large values. If the intervals are unequal, you might find the direct method or assumed mean method more straightforward. A very important point to remember is the concept of consistency. You might wonder, what if I pick a different middle value for my assumed mean? Well, the beauty of this mathematical principle is that regardless of which value you choose from your class marks to act as your assumed mean, the final result for x bar will always be exactly the same. The math adjusts itself accordingly. Finally, let's look at the relationship between the methods we've learned. You can think of the step deviation method as essentially the assumed mean method, but with one extra step. We divide the entire deviation by a constant factor, h, to simplify the arithmetic. It is simply a more refined version of what we studied previously. Before we finish, I want to point out a few common pitfalls in the next slide, so please pay close attention to those. Common mistakes to avoid. First, the most frequent error I see is forgetting the multiplier. H after you have calculated the sum of f sub I times u sub I, divided by the sum of f sub I. Many students are tempted to add that result directly to the assumed mean. Remember, you must multiply that entire fraction by the class size. H, before adding it to A. If you skip this step, your mean will be much smaller than it should be. Second, be very careful with your calculation of u sub I. This is the step in our step deviation method. You must perform the subtraction of the assumed mean from the class mark, which is x sub I minus a, and only then divide that result by the class size, h. Also, pay close attention to your negative signs. When the class mark is smaller than your assumed mean, your u sub I will be negative. A single sign error here will cascade through your entire table. Third, double-check your class marks. X sub I, as we saw in our earlier examples, the class mark must be the exact midpoint of your interval. If you miscalculate even one midpoint, every subsequent calculation in your u sub I and f sub I times u sub I columns will be incorrect, rendering your final result invalid. Finally, do not confuse your frequency, f sub I, with your class mark, x sub I. When you are filling out the final column of your table, you are looking for the product of the frequency and the step deviation, which is f sub I times u sub I. It is easy to accidentally multiply the class mark by the step deviation instead. Always take a moment to verify which column you are pulling your numbers from. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even when you understand the logic of the step deviation method, it is very easy to make small arithmetic slips that can lead to the wrong final answer. Let's look at 4 specific mistakes you should watch out for. If you stay vigilant and avoid these 4 traps, you will find this method to be an incredibly powerful and efficient tool for handling large datasets.